So, we will continue where we left on the derivation of impedance. Just to refresh your memory, earlier we have seen that you have tried the fixed equation, we have tried the current equation, and under steady state conditions you can solve them and get the concentration profile, concentration on the surface as a function of potential, and at a given potential you can also find the concentration profile, it is going to be linear. Okay. And you can also find how the current varies as a rotational speed of the electrode changes. So, as the rotational speed changes, you have different boundary layer thicknesses and you have different current profiles here. Then we started deriving the equation for impedance. So, we want to get an expression of IF AC in terms of EAC and other values. So, instead of expanding in terms of EAC on the right side, we expand it in terms of del E, del CA and del CB, and in order to get the del CA and del CB, we were solving the fixed equation. So, if you write the fixed equation for del CA, we can write it in terms of amplitude or magnitude and phase at a given omega t. Okay. So, when we do this, we get a ordinary differential equation in terms of the location for C A tilde, where C A tilde is C A 0, it's the phase C A AC 0, you can write C A AC 0, okay. Phase and magnitude of the amplitude. So, if I have to draw it, I would say this is the electrode surface, this is the boundary layer, and beyond this the concentration is fixed here, and if there is no DC bias, concentration throughout this is going to be straight. When we apply in AC, concentration on this surface is going to fluctuate with respect to time. If there is a DC bias, it may look like this, and if you apply an AC on top of it, small AC, it is going to fluctuate around this. Out here it is going to fluctuate, out here it is going to fluctuate, meaning it is going to oscillate, and in general it will not have a phase in sync with the AC potential. It will have a phase offset, and that depends on the omega value, it depends on where that is, but we are interested in finding the concentration here and the fluctuations in the concentrations on the surface, because we want to know how the current is going to be affected. Reason is we can measure only the current, we will not be able to measure the concentration fluctuations at any location. So, we want to estimate how this is going to be. So, what we get is an equation ODE, and it is a simple ordinary differential equation, second order ordinary differential equation. We can write the auxiliary equation. So, we know how to solve this. You are going to write, normally you will write this has two roots, right, plus or minus m. So, since we use C for concentration, we are going to use A1 and A2 as the integration constants for the oscillations in species A. For oscillations in species B, we are going to write it as B1 and B2, and we are going to write it as e power mx, e power minus mx, because plus or minus m are the roots of this equation. Now, we want to get the integration constants A1, A2, and likewise we will solve it for the B1, B2. Actually, we will not solve it, I will just tell you this is the solution, but if you know how to solve it for species A, you can solve it for species B also. So, we have fixed equation, we have boundary conditions. Okay. We are looking only at the surface, we want to get the concentration at the surface, but in general this equation is valid throughout this boundary layer. Now, we will get it for two cases, one is a finite boundary layer thickness, another is infinite, it is called semi infinite because it goes from 0 to infinity. Okay. So, where the solution is not at all stirred and that dimension is large enough for us to consider it to be semi infinite. So, we have two boundary conditions at x equal to delta in case of finite boundary condition, right, and when x tends to infinity is the semi infinite case. Those cases we say at that location concentration of A is going to be fixed value, it is going to be Ca bulk, and concentration of B is also going to be Cb bulk, it is not changing. On the surface we can relate the current, Faraday current, to the flux of species A and B. Okay. So, in this case we are going to say anodic current is positive. So, this is reaction A going to be with an electron. So, when you apply positive potential, anodic potential, more A will get converted to B, and we are going to say that current is a positive current. Okay. That means, now imagine this is location 0, this is location delta, delta or infinity wherever that is, and this is electrode here. If A is getting consumed, originally let us say this is the concentration of A throughout the solution. Okay. If I give positive potential, A is going to be consumed, that means A concentration of A here is going to be less than the concentration in bulk, and concentration of B is going to be more than the concentration in bulk. Right. If I apply a anodic potential, this is how it is going to look like, and when this is the case, what happens to dou Ca by dou x? That is a positive value, because it has a positive slope. Increasing x gives us increasing concentration of A. So, dCA by dx is positive, diffusivity of course is a positive number, and that is going to be equal to IF by F. In general, it is going to be IF by NF, where n is the number of electrons. This particular example we are keeping n equal to 1. So, if you know how much current is coming, we can also say what is the flux of species A, because 1 mole of A will give us 1 mole of electron, and 1 mole of electron, when you use the factor F here, Faraday constant, it tells us how much current is coming. So, we are able to relate the current to the flux of A, and we can also relate to the flux of B, because 1 mole of A gives us 1 mole of B here, and concentration of B is decreasing here, that means dCB by dx is negative, because we choose the convention that anodic current is positive. So, when we solve for species A, we are going to use this condition at x equal to 0. When we solve for species B, we are going to use this. Now, you have an expression for Ca tilde. This is in terms of Ca, and this is also in terms of Ca, no problem. We want to convert this boundary conditions in terms of Ca tilde. Now, at x tends to infinity, we are going to first look at semi infinite boundary conditions and solve for that. Later, we will look at finite boundary conditions and solve for that. Okay. At x equal to infinity, Ca is Ca bulk, Cb is Cb bulk, that means Ca AC, there is no fluctuation there. This is one way of expressing it. This is another way of expressing CAAC. This is another way of expressing CAAC. Fluctuation is 0. We can write in terms of sign. We can write in terms of e power j omega t plus phi a, but then we also know we have grouped this and e power j phi a as Ca tilde. So, in the bulk there is no fluctuation, that means CAAC is 0, Ca tilde is 0. The expression here, if x equal to infinity, what happens? This goes to 0, this goes to infinity, and yet if I want to say Ca tilde is 0, that means A1 has to be 0. Does it make sense? We want to find A1 and A2, and we have two boundary conditions. One of them is at x equal to infinity, another is at x equal to 0. So, we get the constant A1 as 0, only then we can satisfy the boundary condition that as x tends to infinity, concentration is a fixed value. Second, we want to write dou Ca by dou x equal to If by f divided by diffusivity dA. So, we want to use the second boundary condition. Now, under steady state condition Ca dc or Ca steady state, and a fixed dc potential, we know this is valid. So, Ca in general we can write it as Ca steady state plus Ca AC or Ca dc plus Ca AC, and If we can write it as If dc plus If AC. So, whatever we have written here we can write it for AC component only, and when we write for AC component we are going to write now If AC, another notation is del If, and in general it is going to be If AC 0 e power j omega t plus phi I, where I phi I indicates the phase difference between the current and the potential, and that is going to depend on what the omega is. Now, just like we have done it for Ca, we can also say that If AC can be written as where If tilde, it just makes it a little easier for us to do the calculation, that is all. So, we can get rid of the time factor from this, that is all that is there. So, in del If by f we will write it as If AC by f, and that is going to be If tilde e power j omega t by f. E power j omega t basically goes away, it gets cancelled from this equation, j phi a only, the j omega t comes out. So, I have taken this equation, write it as If AC 0 e power j omega t multiplied by e power j phi I. Leaving out the e power j omega t, the remaining terms are collected and kept as If tilde, because on the left hand side of this boundary condition you have e power j omega t. I do not need to do that, okay. This is just one way of expressing it. I can just write it as If AC 0 e power j omega t e power phi j phi I and leave it as it is and just cancel the things, but then every time I had to write a lengthy expression. I had to write If AC 0 e power j omega phi a. Instead, I want to just write a little shorthand for that. So, you have an expression for Ca tilde, take the derivative of this. Here you have the expression for Ca tilde, take the derivative with respect to x. We already know A1 is 0, therefore, we do not have to keep this. If we take the derivative here, what do we get? We would get A2 multiplied by minus square root of j omega by dA multiplied by e power whatever that is there, right, e power mx. If you take derivative with respect to x, you will get m multiplied by e power mx. So, I want to take the derivative and substitute it there. We would say A2 minus square root of j omega by dA, right, e power minus square root of j omega by dA into x. Now, I want to evaluate this at x equal to 0, then the e power mx or minus mx becomes unity. So, I would write A2 multiplied by minus square root of j omega by dA, that is going to be given by IF by dAf. I have just moved the dA to the right hand side of this boundary condition. Essentially, we want to find the value of A2 and substitute it there. A2, it will be nice if it comes in terms of EAC or IAC. Likewise, B1, B2 we have to calculate. I can tell you right now B1 is going to be 0 and B2 is going to look like this, except because the boundary condition says negative. So, in terms of the boundary condition at x equal to 0, we have dA dou Ca by dou x at x equal to 0 equal to IF by f, and that is equal to minus dB. So, you would get the constant B2 just like A2 with a negative sign. So, you are able to get up to this. So, we will rearrange it and we write A2 as minus IF tilde divided by Faraday constant. We have one factor of dA, another factor within square root, and after rearranging you would get j omega dA. It is just an algebraic arrangement of that. Therefore, we would write Ca as, substituting for A2, you would write Ca tilde, in general it is going to look like this, and Ca tilde at x equal to 0 is going to look like the first factor, because the second factor is going to become unity. Once we know Ca tilde, we can write del Ca. All that we need to do is to multiply by e power j omega t. And now that IF tilde combined with e power j omega t, you would get it as del IF or IFAC. So, this is how it works. The boundary condition, it says current is related to the derivative of concentration, because derivative of concentration gives us the flux. Concentration, it is a concentration gradient, right, derivative of concentration with respect to space, it is not derivative of concentration with respect to time. So, concentration gradient is going to tell us how much material is coming, and how much A is coming tells us how much electrons are being produced. How much A is consumed tells us how much electrons are being produced. Now, potential is sinusoidal with respect to time. Current is also going to be sinusoidal with some phase difference, let us not worry about it. Let us just restart it and say, when current is going like this, we will say when the current starts as 0, we will call that as origin, just for now. Okay. So, current is going to be sinusoidal with 0 phase now. Now, if current is sinusoidal with 0 phase, concentration is not going to be sinusoidal with 0 phase. Concentration will be sinusoidal, but actually the derivative of concentration with respect to x, that only is going to be in phase with current. So, what we end up getting is, because of that, and this is going to be e power square root of j omega x, we get the derivative, you get a j omega term within the square root here. Concentration will have an offset with current. Concentration gradient will be in sync with current, and obviously current is going to be in general out of phase with potential. So, all these three with respect to potential, current and concentration of A, concentration of B, they will in general have a phase difference. Even if current and potential are in sync, concentration will have a difference. So, because the concentration gradient is related, because its mass transfer limited or mass transfer plays a role, we have a little more complex expression here. Now, del Cb is going to look like the same as del Ca, except that it has a negative sign, because the boundary condition says If by Nf or If by f equal to minus dB dou Cb by dou x. at x equal to 0. So, if you go through the derivation, it will look the same except that the sign is different. So, we will not derive it, we will just say that this is the correct expression. So, del E is EAC, del CA is written in terms of del IF, del CB is also written in terms of del IF, and everything else is known to us. So, we will go back to the expression where we write del IF, its IFAC is dou I by dou E multiplied by del E, dou I by dou CA multiplied by del CA, dou I by dou CB multiplied by del CB. And we already know that dou I by dou E multiplied by del E is given in terms of EAC and other known factors. We had done this before. Derivative of current with respect to concentration of A and B are also known to us. So, we are going to substitute and rearrange. What we want to get is or the inverse of this, and on the right hand side everything else should be known to us. So, what we used to get previously was del IF on the left side or IFAC on the left side, all the things on the right side will be grouped together and you will get EAC. In this mass transfer based derivation, on the right hand side one of the expression has EAC, other expressions we brought in terms of IFAC or del IF, and we are going to rearrange it and finally still get the expression for EAC by IAC. So, this part del CA is negative IF. For the second part, it is minus FK1 DC multiplied by plus IF. So, these two actually will have negative sign when you arrange everything, and then you bring it to the left side, you are going to get del IF on the left side, and when you bring this term to the left side, it is going to look like plus F K1 DC by F. Of course, F will cancel out, that is why I marked them in blue. On the right hand side, we are just left with this. Then take the ratio of del IF by EAC, you are going to get 1 here plus K1 DC divided by square root of j omega dA, K minus 1 DC divided by square root of j omega dB. Does it make sense? It is okay. So, this is the expression for semi infinite boundary layer thickness, and this will simplify when you have EDC equal to 0. That is, when DC potential, there is no bias in the DC potential, whatever is at open circuit potential, we are going to leave it at that. So, the admittance form is written here, impedance is just going to be the inverse of that. Now, this is written separated into 3 components. One is written as RT, okay. There is no omega in it, omega dependence in it. Second is written as Warburg impedance for species A. Third is written as Warburg impedance for species B. It is not that well separated, but if you look at the numerator, yes, one of them is dependent on diffusivity of A, one of them is dependent on diffusivity of B. But the denominator, you have concentration of A at x equal to 0, concentration of B at x equal to 0, and they will depend on diffusivity of A and B. But leaving that aside, you can separate this into 3 components, one called charge transfer resistance. Charge transfer resistance is basically Faradaic impedance at infinite frequency. At infinite frequency, the terms colored in blue and green will go away. Therefore, what is left is charge transfer resistance. So, numerator red color, denominator of course, it is common for all these 3, and often we will write diffusivity of A is roughly equal to diffusivity of B, but right now we are not going to do that, we will just keep it as it is. I want you to notice the following: when you have semi infinite approximation, you cannot say that you have steady state with a DC bias. Moment you apply a DC bias, EDC is not 0, it will never reach steady state, because concentration at x equal to 0 you have to find it, and concentration at x equal to infinity is bulk. Concentration gradient is never going to be non-zero, because you are going to write concentration gradient as but delta is going to be infinity, and this will become, as you increase the EDC or as you increase the delta even in finite boundary layer thickness, this is going to become lower and lower value. The lowest it can go to is 0. Concentration of A cannot go below 0, concentration of any species cannot go below 0. So, you will never be able to get a non-zero value under steady state condition, and if concentration is really 0, you will not have any reaction, any forward reaction, right. So, when you say that the boundary layer thickness is really infinity, then you cannot have any potential that is other than, you cannot have any DC potential that is other than 0 and expect a steady state concentration profile. You can have unsteady state concentration profile, no problem. You can have a sinusoidal fluctuation and expect steady periodic variation, that is still okay. What you can't say is I will go to 0.1 voltage with respect to OCP and maintain that and wait for some time, I will get steady state, you will not get that. So, in this case we are going to restrict ourselves to finding the impedance only at EDC equal to 0. Now, RT depends on the concentration of Ca and Cb at the surface. It is not completely independent of mass transfer. Concentration in general, okay, when we come to finite boundary layer thickness, it becomes important. And likewise, if you look here, ZWA and ZWB depend on K1 and K2, sorry, K1 and K minus 1, and they are not exactly independent of kinetics. However, if you look at the special case of EDC equal to 0, concentration of A on the surface is going to be same as concentration in the bulk. Concentration of B on the surface is same as concentration in the bulk, because we are not applying any DC bias. Okay. K1 DC is going to be K1 0, K minus 1 DC is going to be K minus 1 0, because EDC is 0 here. And
when we do not apply a bias, there will be reaction happening.
There will be reaction happening. Net reaction is 0, net reaction rate is 0. Both reaction will happen at equal rate, both may happen at a fast rate or both may happen at a slow rate, but net reaction rate is 0.
So, if you have an irreversible reaction, then
you can't have a reversible reaction and expect equilibrium. This potential, open circuit potential here, is the equilibrium potential, because there is no other reaction. You can have two different reactions, A going to B and C going to D, and still one of them may give positive current, another may give negative current, and you may get net reaction, net current to be 0, not net reaction. That is a different case, but here we are considering A going to B and B becoming A. We can say that we are going to apply a positive potential or negative potential. When you are going to shift away from the equilibrium here, we can get steady state condition as long as the boundary layer thickness is restricted. Finite boundary layer thickness, I have a large reservoir of A and B, where I am maintaining concentration of A and B. Here I can have steady state, not equilibrium. When I apply a DC potential, I will continuously consume A and produce B, and they are going to go away. Once it comes here, beyond that boundary layer, it is all completely mixed, well mixed, and there is no change in the bulk concentration, because it is a very large reservoir. That is a possibility. In fact, if you take a normal cell, put for example 200 300 ml of solution, put a small electrode and control the rotational speed, it will give a finite boundary layer thickness. You can have a reaction of A going to B. In fact, the counter electrode is typically B going to A. So, whatever small amount you consume here will be produced on the other side. leave that aside. If you are consuming small amount here and producing small amount of B, but you have a large reservoir, in 5 minutes or 10 minutes you are not going to really change the concentration of the bulk. Okay. So, when you look at this, we can write the expression B 1 K 1 dC minus B minus 1 K minus 1 dC at multiplied by C B x equal to 0. This B 1 is actually alpha f by R T, this is K 1 dC, this is C A at x equal to 0, and this is going to be B minus 1 K minus 1 dC and C B at x equal to 0. And after rearranging, K 1 0 and K minus 1 0 are not completely independent, they are related. So, the moment you specify C A bulk, C B bulk and K 1 0 and then say I am going to take equilibrium potential as the reference potential, 0 potential, then these are related. So, I can write K 1 0 C A bulk, I can write K minus, okay, it does not like it if I write here. I can write it as K minus 1 0 C B bulk, both are equal actually. So, I do not need to make the assumption C A bulk equal to C B bulk, I will still get this expression. So, under this condition, it looks like this part does not have any diffusivity component here, this part does not have any kinetic component K or K minus 1 or K 1, this part does not have any kinetic component, right. So, you would get the feeling that R T is independent of diffusion, ZWA and ZWB are independent of kinetics, but it is not always going to be clean separation, it is valid only at equilibrium. Now, this can be written in a little more elegant form. It is commonly written in textbooks in this form, where you write a parameter sigma as 1 by square root of 2 R T by F square, this R T by F square comes C A bulk square root of d A, C B bulk square root of d B, and you would combine Z W A and Z W B and write it as and many times diffusivities are not very different, people would write d A equal to d B, becomes lot simpler. It will become, if C A bulk and C B bulk are equal and d A and d B are equal, you are going to just write this expression as diffusivity, which is A or B, it does not matter. So, you will get simplified form. So, you will end up getting square root of 2 by j omega as the remaining factor here. Square root of 2 is introduced here, so that the numerator gets square root of 2, and when you do this you can write it as 1 minus j. Okay. J is actually written as e power j pi by 2, and you can get this square root or 1 by square root by looking at this. Square root of j is going to be e power j pi by 4, it is going to be cos pi by 4 plus j sin pi by 4. 1 by square root of j, similarly you can find that it is going to be cos minus pi by 4 plus j sin minus pi by 4. So, you get 1 minus j, except that you got square root of 2 as the factor, cos pi by 4 is going to be 1 by square root of 2. So, this expression gives you a feel for how it will look like in a complex plane. Okay. Sigma is a constant for a given condition at a given temperature, given diffusivity, given concentration. Sigma is a constant. Omega is what we vary. It is going to look like a line, 45-degree line, 1 minus j with the difference, 1 here is the real part, j is the imaginary part. So, it is like writing y minus x by square root of omega. When I decrease the frequency, this number becomes larger number. So, when I decrease frequency, it becomes larger number. When I increase frequency, it becomes a smaller number, smaller factor, but the ratio it is always 1 minus j, it is always a 45-degree line. So, this is going to look like a 45-degree line with decreasing frequencies going towards larger value. The total Faradaic impedance is given by RT, charge transfer resistance, plus Warburg impedance, and we are able to write in a clean separate form only under the special condition. It is a simple electron transfer reaction, and we are at ED is equal to 0. And I just want to mention there are other methods using Laplace transform. There is another method, there are probably few other methods where you can get the same expression. You should get the same expression at the end, but typically you get expressions like this for finite as well as semi infinite boundary conditions. You get expressions like this given in the book. Some books give you also the previous expression, which is little more general, but do not assume that RT will not vary if you change the DC potential. This gives you the feeling that RT will be dependent only on K10 and Ca bulk and temperature, but that is valid only at equilibrium. When you change the potential, RT will change, and not only that, it does depend on diffusivity. In this special case, you can rearrange and get certain equations substituted here, and then you can get this value here. And when you look at the RT, when you look at the CDL, solution resistance is 0. So, I have made up some numbers here, K10, K minus 10 is some numbers, EDC is of course 0, C and Cb bulk I set them as 5 millimolar, charge transfer coefficient is half, temperature at 300 Kelvin, double layer capacitance as 20 microfarad per centimeter square. This is how it will look like. I denoted Z omega or Z omega as Warburg impedance. I can also represent bounded Warburg impedance when delta equal to finite value, I can set is BW. This is a 45-degree line only if you do not have anything else. Here of course, you have solution resistance not here at 0, double layer capacitance is there and charge transfer resistance is there. So, from here onwards it looks like a 45-degree line, and depending on the values it may look like this. At very low frequencies it will look like a 45-degree line, but here it is not a 45-degree line, it is shifted origin, shifted by R solution and RCT or RT. When you plot it in Bode plot, you should also have a feel for how it will look like. Magnitude at low frequencies keep increasing. So, you have one loop and then the second loop. Phase value starts at 90 here, this is not 45, it goes to little less than 45 here, because its origin is shifted. If you go to larger and larger value of impedance or lower and lower frequency, this would tell that it will be approaching 45. Of course, if this is very very low, it will again approach 45. And if you look at Z real and Z imaginary, you get one loop in the Z imaginary, imaginary goes up, comes down and then it increases, goes up, comes down and then it increases as the frequency decreases. Real part of course moves up and then somewhat settles and then moves again. So, real part increases, remains somewhat constant and then increases again. So, this is signature for you to look at either in complex plane plot or in the Bode plot.
So, all this is for semi-finite delta, right?
Yes, semi-infinite delta. We have not solved it for finite condition yet. and we will probably have to postpone it for next class. All this is done for simple electron transfer reaction. When you have one adsorbed intermediate, when you have two adsorbed intermediate, none of this formula will work, and you can't just take the expression for Faraday impedance and then put a W there, add a Warburg impedance there, although some people sometimes tend to do that. Okay. It is possible actually to derive the expression. It is very complex. So, I will just tell you a brief story and then leave it. Okay. In 1960s, S.K. Rangarajan, okay, he was a former director of SICRI. He derived some expressions for small amplitude, large amplitude conditions for general, not for one reaction. Okay. He was actually BSc mathematics person. It is not PhD, he was not in electrochemistry, and at that time the SICRI director contacted him. He was actually a mathematician. In the beginning he started his career as a movie critic. Then okay, he went to academia and he gave a problem saying okay, it will probably take a year, and he solved it in a day. It is like a Ramanujam. It is a very high level mathematics, very simple elegant expressions, but then to actually derive that and solve, you will have to spend a lot of time. Normal people will have to spend a lot of time to do. So, after 50 years an example paper came to say you take this reaction of EAR, where you have one electron transfer reaction and one adsorption reaction, which we have seen, right. We can derive the expression for kinetic limited case without any problem. It gives you a negative differential impedance, but if you use the matrix form that he has given, you get expressions like this. Each one of these, again, what is this, what is this, etc., it goes through many expressions. What it means is it is possible to derive, but it is extremely complicated and lengthy. And to tell you, I have not derived this yet. I am aware that it is possible. Okay. If you can understand what is done for electron transfer reaction, that is good. I am not expecting that you would be able to derive for more complex cases, but you should be aware that it is not as simple as writing the kinetic limited Faraday expression and then putting one more term there. These are interrelated. Basically, the boundary condition where it says this concentration flux is equal to the current in one of the terms. Species that is coming here may not directly give you electron transfer, it may adsorb, and after adsorption next step it may give electron transfer reaction. So, the current may not be directly related to this, current may be related to adsorbed species, and then the adsorbed species concentration may be related to the flux, but they are coupled and you can't normally separate them out. Okay. We will stop here. What we will do next is to derive the expression for bounded Warburg impedance, and after that we will go to what is called CPE, constant phase element. Okay. We will stop here today.